All right, welcome everybody to our second webinar in our webinar series. On this webinar, Christopher Liljenstolpe, give it
Close enough.
Close enough.
Close
Okay.
enough. An E for effort.
The sad thing is I'm actually from Minnesota as well, and I just don't can't pronounce Minnesota names. Is we talking about Kubernetes, and I think we all know Kubernetes is great, and we want to be cloud native, and we'll be able to access all this great technology. But what about the legacy technology, and how do we access things like AS400s or Commodore 64s? Just to put you on the spot, not that I'm trying to put my Commodore 64 back up. For those of you that are not familiar with Chris, Chris is the CTO here at Tidera and has extensive experience in networking, ranging from working at Metaswitch to Big Switch to Telstra, Alcatel, many others. And of course, you chair multiple IETF working groups. Is that correct?
Yeah, on my weak moments.
Your weak
correct.
Okay.
All right. I didn't duck fast enough.
With that, I'll just pass it over to you. Your jokes are far better than mine, so.
It's not hard. Okay, so for those of you, I'm not sure how many folks here saw the last webinar, so maybe I'll give a brief synopsis of what we talked about the last time, because we're going to sort of what we're going to talk about today is continuation. So we talked about yesterday, or the last webinar, was not yesterday. It seems like yesterday, but not yesterday. So what we talked about in the last webinar was how this new microservices or cloud native or scale out kind of environment really challenges the classical mechanism we had for networking workloads, and more importantly, providing protection and network isolation and segmentation to those workloads. Today, the buzzword is microsegmentation or nano segmentation, whatever you might want to call it. But the concept is one that's been around for a long time. You have workloads in your data center, and there's an old joke in the security industry. Perimeter security is sort of like a medieval knight. Hard, crunchy outside, soft, chewy inside. If all you do is draw a perimeter around your network, anything that gets within that perimeter then has free reign within your infrastructure. And there's been a number of fairly large breaches over the last number of years where there have been penetrations into infrastructure past that perimeter boundary, and then that agent or that threat that's gotten inside that perimeter basically can spend as much time as they want mapping out the infrastructure, figuring out where the high value targets are, and exfiltrating the data, because there is not a concept of zero trust within that perimeter boundary. If you're within the walls, you're trusted. If you're outside the walls, you're not. And in today's world, that is probably was never a good model, and it's definitely not a good model today. Today, as we think about the way people build applications, we're pushing code fairly frequently. This isn't necessarily just malicious code; it could be bad code, bugs, etc. You're pulling code that you're using to build these components from a wide variety of sources. You have a lot of people working on this that all can have potentially compromised machines, etc. There's just a number of ways threats can get in. So really, if you want to protect the environment, you not only need to protect the workloads from the rest of the world, you need to protect the rest of the world from the workloads. So that's a zero trust model, or I'm going to defend the outside, defend everything else from the workloads, as well as defending the workload from everything else. So when you start thinking about that, you then have to address how you're going to do that. And we talked about this in the last webinar, and Mike, maybe we'll put in the comments here a link to that webinar if folks want to go back and review it. But the idea is simply that in the older days, in a long time ago, 5-10 years, most application traffic was north-south. you had a silo, you had a customer ordering application, you had a billing application, you had whatever the application stacks were, and most traffic came north-south through that into those applications. So applications didn't talk to one another. So you could basically say application A shouldn't really talk to application B, so you put application A in a boundary and application B in a boundary and application C in a boundary. That's great until you need to start having things in application A talk to things in application stack B. And that's what we call east-west traffic. And what we've seen now over, in this evolution is the vast majority of traffic in data centers now is east-west, not north-south. It's not a query comes in, all the traffic is basically query coming in, you work on it within an application, and you return the result to the requester. The request comes into one application. That application fans out a lot of subsequent requests to other components and other applications, and eventually what comes back is a result, gets assembled back into a result and returned to the requester. So you might have 50% of your traffic east-west between application stacks, and 50% going north-south, and frankly, probably even higher. Maybe it's 90% east-west and 10% north-south. So I now have all these different application stacks talking to one another. So I now need to have a better way of providing isolation. So people started doing that with firewalls. You stick firewalls between your applications, and then you set these fairly static application components, have IP addresses, and you manage the intermediate firewalls IP addresses, use IP addresses to identify those workloads and say, this thing in A can talk to this thing in B. That's great if your environment's static. If your workloads only change weekly or monthly, if they're on servers, if there's hundreds or thousands of application endpoints, that's possibly manageable. It's not great, but it's manageable. But if you talk to most organizations, I'm sure everyone here on this call is in perfect shape, but there are organizations out there where firewalls are a huge impediment to getting applications rolled out. I can stand up a VM, I can load a piece of code, but it takes me a day and a half to get a firewall rule updated to allow that to talk. Or an application goes away, no one updates the firewall rules, and 5 years later you look in the firewalls and say, okay, which of these rules are still needed and which of them aren't needed? And which of them potentially are introducing now vulnerabilities because those addresses have been reused or whatever else. So even in a static environment, these firewall-based infrastructures were problematic. As we now get into environments like Kubernetes and container environments in general, we go from hundreds to thousands of endpoints within your data center or workers to tens of thousands, hundreds of thousands, or even millions of containers in a cluster, in a workload, in a data center. And those containers or workloads might only exist for seconds or minutes or maybe hours, but they're definitely not long-lived like VMs or bare metal servers were. So now I have a lot more endpoints. They're now functionally tighter scoped. So now instead of a big monolithic piece of code, that monolithic piece of code has been split into a number of individual components they're using the network to communicate versus communicating internally in the application. So now I have this issue where it's a much more dynamic environment and I have a much larger number of endpoints. And the way that dynamic environment works is these orchestrators like Kubernetes really treat all of the infrastructure as very fungible and generic. An IP address is just something to be assigned. It has no special meaning or context. It's actually fairly difficult to tell Kubernetes, for example, that this pod should get this address and this pod should get this address. You can do it, but it constrains Kubernetes. And if you go back and listen to the previous webinar, we'll explain why that's really not a good idea, even if you try and do that. So now you're faced with an issue where IP addresses are fungible, workloads come and go constantly. Updating those firewalls becomes now, for all intents and purposes, almost an impossibility to make this work. People have tried various ways of continuing that historical, I won't use the other term, that historical model, but that's not really a cloud native or a scale-up way of doing things. So what we talked about in the last webinar was how you might do this for a container-based environment or a scale-out or cloud-native environment. And the idea is simple. The idea is simple, the implementation can be interesting, but the idea, and by the way, this is our mascot, but it's unfortunately in the way. So actually what I'll do is I'll spin him over here so he can correct me if I'm wrong on anything. So what you do is you attach metadata to workloads. And this isn't just for networking and network policy. This is also for all the other functions that you use in a containerized environment. This is how Kubernetes knows what services have been created, what workloads are offering what services, what stage they're in, etc. So you attach labels or key value pairs to workloads. This is a standard concept now. So you might have labels like stage. I've been told I need to write larger, so stage prod or stage dev. You can have, location Germany or location US. You can have application cust order or application geolocate. And these kind of labels are attached to workloads. So here in this, we're not going to draw servers and all that stuff because that's basically just, I did that in the last one. We talked a little bit about it, but for right now, we're really just talking about workloads in an infrastructure. How those workloads are embodied. Are they on microservers? Are they on one honking big server? It doesn't really matter. These workloads now have labels on them. So maybe this workload has stage prod, location Germany, and app customer order. And this workload has stage dev and location US and application customer order. And this one might have stage prod and location US and application geolocate. Okay? And it doesn't matter if there's one of these or a million of these or however many much. These are just workloads in the infrastructure. Now what you can do in a more cloud native environment is instead of trying to write firewall rules saying, this thing has to be in this subnet, and this has to be in this address range, and this has to be in this address range or VXLAN, and then say which of those ranges can talk to which, you can create more generic policies. You can say, you can have policies, I screwed myself here, things labeled stage prod are allowed to talk to stage prod on port 443. So workloads labeled stage prod can talk to other workloads labeled stage prod on 443. I'm going to erase my cloud and sort of scope it down here a little bit more. Workloads labeled stage prod, or now workloads labeled application cust order are allowed to talk to applications geolocate on 8080. Because application geolocate is sensitive and location sensitive, what you may actually say is application geolocate will only allow things, application geolocate and location Germany will only allow from application customer and location Germany, port 8080. And so in this case, this rule, application customer order, is allowed to talk to applications geolocate on 8080. So in this case, this workload is application client and application customer, location US. It believes it can talk to, I'm going to change this to make it more interesting, B. So it believes it can talk to application geolocate located in Germany. That's what this policy would allow. So does this workload. It's located in Germany. It's an application customer order. It believes it can also talk to that workload. There's no IP address here. There's nothing in this that's specific to an instance. This is data. These are labels that are attached when these workloads are created in the pod spec or whatever you're using to manage your workloads, say Kubernetes. However, and the other thing is you now have a bunch of policy rules. They're not IP address rules. They're not infrastructure based. They're just basically saying things that are production should be able to talk to things labeled production. Things that are application customer order should be allowed to things talking to geolocate on the geolocation port 8080. However, there's restrictions in Germany that the geolocation information can only be reached by other things in Germany. So in this case, this is policy. Now a network policy enforcement engine, say in Kubernetes, can now render these such that this communication from the United States customer order system, this should, its policy says it should be allowed to talk to here. However, this workload, because it's in Germany, has a more restrictive policy, and it says that communications, if they're not from Germany, will be blocked. This is a zero trust model. This guy believes he should be able to talk. This one enforces a rule that it's not allowed. Whereas in this case, this same kind of workload, except it's in Germany versus the United States, it believes it should be able to be allowed to talk, and the workload on the other side says that it indeed should be allowed to communicate. So in this case, this communication is allowed, and this communication is not. So this is how you start thinking about microsegmentation in a cloud-native world or in a scale-out world. And again, I give a more complex example of multiple interrelationships and the cross-products can come from that if you try and do this in the legacy, I use that word, approach, but this gives you an overall concept. So this is great. So now there's no firewalls in here. This is supported by the underlying infrastructure. And in fact, at Project Calico, what we actually do is enforce these rules right in front of the individual workloads within the underlying Linux kernel, and dynamically update those rules at orders of tens of milliseconds as the infrastructure changes. So that's how we do this. So the world is good. We've solved the microsegmentation problem. It scales really well. It's now much more developer friendly because the developer doesn't need to think in terms of IP addresses and things that are now very fungible. They just think in terms of what's their policy, and security teams, et cetera, now think in terms of policies and labels and if you want to think of it, personalities of components rather than specific instance information like IP addresses or VX lines or IP ranges. However, there aren't too many people that are greenfield cloud native. For those who are greenfield cloud native, this works. You're done. You can go have fun and write your applications and be merry. Unfortunately, many people have lots of legacy stuff in their infrastructure that they're not going to be able to just burn down and walk away from as much as they might like to. I've worked at carriers before, and I had customer databases that were based on the original national numbering plan, phone numbering plan. And those databases sat on mini computers and were 40 years old, and that was still the customer record. So therefore, you have to use it. If you ever wondered, if you live in certain geographies in the world, why you must have a phone number, have a phone for a service that has nothing to do with phones, say cable or whatever else, might be because they need that phone number because that's your customer record ID. But we won't go into that. So now, what do you do with those legacy environments? Because those legacy environments don't have Kubernetes running them or some other container orchestration system. They don't have labels. They may not even have VMs. They may be legacy hardware. So what do we do to bring those legacy components into this world so that you don't have this horrible impedance mismatch of a very flexible environment within here and a firewall-based infrastructure on the other side? So let's walk through what might happen here. So let's give myself a little more room. Those rules will still be the same rules. And here's my cloud. I'm going to switch colors because I think the black is wearing out a little bit. But now I've got this database over here, and I've got some legacy server running Linux over here. And this is some form of appliance. I have no access to the kernel there. Here, this is a standard Linux box running some code. I do have access to that. Now, today, there might be a firewall in front of these things. And the firewall is going into the Kubernetes cluster. The firewall, unfortunately, is based on, as all of them usually are, IP address rules. So it might be CIDR block A is allowed to talk to appliance, or CIDR block X is allowed to talk to appliance A on 8080, and CIDR block Y is allowed to talk to the server B on 443. So that's what you used to do. And the things that need to talk to this were in subnet X, and the things that were in need to talk to this were in subnet Y, and that worked. Remember what I said earlier, Kubernetes has no real concept of pinning addresses or creating snowflakes of addresses, saying this thing should be in address range X and this thing should be in address range Y. Doesn't really have that. You can do that, but it brings with it all sorts of pain. Watch my earlier webinar. So we have to come up with some other way of dealing with this, because otherwise, what our option is whenever workloads get created as scale out or blue-green testing or whatever other things, new code deployments, somebody's going to be having to update these things really, really quickly to handle these addresses. And these things might only last for seconds or minutes or hours. So automating this, you now need to automate this. And more importantly, you need to automate this with a bunch of non-contiguous addresses. So if this is some kind of hardware, you now have a huge list of IP addresses. You have some way of updating those in potentially seconds, for only seconds before you pull them back out again. And two, each of those entries might be consuming a TCAM entry. For those of you who understand TCAMs, it's a limited space, it's a high performance memory in a lot of filtering hardware and routers and switches, but it's usually a limited environment. And what we have seen is customers in exactly this boat where they've had to turn off customer acquisition or deployment of new services because literally they exhaust the memory in these hardware appliances. So that's probably not a good idea. And that's exhausting it at 4,000, 16,000, etc. entries. You might be talking about hundreds of thousands of things here. So that's just not going to work. So what we need to do is come up with some other way to manage this. So there are a couple of ways of doing this. Let's first of all take the easy case, which is I've got this Linux server out here. It's not part of Kubernetes. What you can do, depending on your implementation of, say, Kubernetes network policy, and this is something Calico can do, is you can create a synthetic record for this host. And you can create a synthetic record for this host. So in the cluster, you can actually say there is this B. It has address Y. And it has labels SD, state dev, location US, application, customer order. So I can inject a record for this basically into my Kubernetes environment or into my network policy environment anyway, say it in Calico. So now the rules on these devices, the example I gave earlier, again, let's make this a little more interesting. This is a location in Germany. The rule here that allowed this workload to talk to it, but not this workload, this Linux server has the same characteristics as one of these workloads. So the policies that get rendered will allow traffic from this server, even though it's not in the Kubernetes cluster. And this will allow traffic into this workload. No firewall necessary for traffic going that way. So the only thing you have to do is maintain this sort of static record saying what the characteristics of this server is. But this is a bare metal server. It probably has a much longer life cycle. It might have been there for a couple of years or a couple of months or whatever. This is a day zero provisioning thing. And for these kind of things, day zero happens very infrequently. Whereas here, day zero happens, it's second zero or minute zero, not day zero. So this allows filtering for things coming from the outside in. Same thing, for example, would apply on this path. But now, so this follows the model of I am protecting my Kubernetes cluster from these. It says a VIAT not protecting these from everything else. So there's a couple ways of doing that. One, if this is a Linux server, you can install the Calico agent called Felix on this Linux host. Even though it's not hosting any containers, it's not part of Kubernetes, nothing else, you can install the agent. It doesn't add anything to the data path. It's a user-land agent that manipulates the Linux kernel. And now policies that would be rendered on these endpoints are also rendered on these endpoints. So now, this, for all intents and purposes, this server behaves just as if it was in the Kubernetes cluster or an OpenStack cluster or whatever else you're using with Calico, even though there's no orchestrator managing this. And again, all you have to do is maintain this record as a zero-day provisioning event. So now you have protected this workload from everything else within the Kubernetes cluster, not everything else, but within the Kubernetes cluster, and frankly from other things, depending on what your policies say. Your policies may have a policy that says things that are application customer order, location Germany, are going to allow traffic on port 443 from any address in Germany because this has to be a front-end application. Then anything coming into this platform from addresses other than in Germany, however you've identified those, will be blocked and everything else will be allowed through, as well as anything from the Kubernetes cluster, the inter-application traffic that's allowed. So this can actually protect this from a wide range of threats. Or you could say, I'm only going to use these policies for things that are interacting with Kubernetes, and I'll still use the legacy firewall to deal with the big bad internet up here. So there's a couple different ways of doing that. Similarly, to protect this appliance, you probably still leave the firewall in place to protect it from everything else, because I can't install any agent on here. But what we have seen folks do, in this some of our customers do, is basically say, this firewall here is going to allow any traffic from Kubernetes in. So anything coming from this big IP address range, this pool of addresses that Kubernetes is using, is going to be allowed to talk to this appliance, with the understanding that you will be using egress rules here in Kubernetes, the allow to rules, that basically would then say what workloads are actually allowed to talk to the appliance. So the firewall protects stuff coming from everywhere else, but you're going to rely on this distributed firewall within the cluster, and even this object out here, you're going to rely on them to filter and protect this. You're going to push that protection boundary right to each of those workloads. So this is basically allowing the distributed firewall type behavior that exists to protect this appliance as an aggregate. So in this case, like I said, the firewall says if it's not, you have to go through firewall rules unless it's coming from the Kubernetes address range, allow the Kubernetes address range in, because we know Calico has applied the appropriate egress rules on those workloads to enforce your policy. We've seen people do this private cloud on-prem data center to cluster. We've seen this public cloud to private cloud conversation as well. There are some ways we talk about ensuring traffic is coming from a Kubernetes protected node. That's beyond the scope of this conversation. Beyond the point of it came from the address range, we know what policies have been installed in that address range. So that is a way of thinking. We call this native host protection in Calico. But it's basically the way we can, a couple of different ways, we can apply the same model that we do in an all native and Kubernetes native environment, or Mesos or OpenStack, etc. native environment to more legacy endpoints, and not having to deal with updating these things on seconds and minutes, etc., or going through the fool's errand of trying to create smaller and smaller, more and more scoped IP address ranges to allow for static policies on the firewall. So that's the approach. It's leveraging the same concepts, and it sets you up very nicely if you're going to, over time, be more and more cloud native, because you're sort of walking away from having to build a whole bunch of tooling around these things, which don't really have a play for inter or intra cluster communications at a minimum in the future. So you're sort of advancing this cloud native construct to things that aren't inherently cloud native. And you've probably heard enough from me at this point. So why don't we open it up for questions, Mike? If there are any.
Perfect. So if you do have a question, please feel free to post your question either in the chat or in the Q&A here, and we'll try to stump Chris. I have one quick question. That is, coming from the security standpoint, looking at monolithic or legacy applications, are there inherent risks of opening up, the firewall to everything with Kubernetes? Are there tactics to really restrict that, or how would you go about that?
Well, sure there are. You can, for example, say, first of all, you can have overarching policies in the Kubernetes cluster that say, in sort of a belt and braces, that you're going to deny all traffic outbound to things in this address range that would be otherwise protected by the firewall. So by default, Kubernetes won't allow the network policy implementation in Kubernetes won't allow any traffic to that set of address ranges which you've now opened up the firewall, at least as far as Kubernetes address ranges are concerned. So in that case, you'd have an overarching policy here that says, I block all traffic to A and B addresses. And then more specific policies that say, except for things with these labels, which will be allowed to talk 443. You can further say, the only thing I'm ever going to be allowing from Kubernetes here is, say, port 443 or port 8080 or port 631 or whatever. Maybe there's a little subset. So you basically, I know that from the Kubernetes cluster, these are the only addresses that should be hit, or the only ports that should be hit. So we'll just allow those on the firewall through. So that's a bit of a belt and braces. You just need to remember that if all of a sudden a workload here needs to access a different port, you not only need to write a policy to allow it here, you also need to update the policies on the firewall to allow that new port through. So you now have to remember, it's going to be one of those classic things. I allow it here, it still doesn't work. Why doesn't it work? And somebody has to remember, oh yeah, we need to go throughout the firewall. Did I answer the question?
Yeah, that was very helpful. I think you already covered, but just to recap on the policies on Linux, are you putting Calico on the Linux box to have it connected to Kubernetes, or how are the?
So we installed the local agents. So on that element, which is a piece of code we've written called Felix, which is responsible for manipulating the Linux kernel tables, and it talks back to the Project Calico data store where we maintain the inventory list of endpoints, their labels, and the policies associated with them. So it's not really talking back to Kubernetes specifically, it's talking back to in our case, the Calico data store, which can be part of the Kubernetes data store or it can be standalone.